Good night. We're very close to the morning, something past 11, still night. And I'm here continuing with and finishing up with the first phase of quantum mechanics. And we're going to do our interface and go on to a little bit of electromagnetics and introduction to electromagnetics, and then we'll see where we'll go from there. So without further delay, I'll continue with the ending of quantum mechanics and the interface with electromagnetics, Maxwell equation, Hemholtz equation. And so we start off here with, we said we're going to start off with quantum chemistry, which is none other than molecular quantum mechanics. And here we see now that quantum chemistry, molecular quantum mechanics, a branch of physical chemistry that studies application of quantum mechanics to chemical systems. This uses the quantum properties of atoms. So we are just going to do that definition by audio. We're not going to write it because we want to sort of conserve on the paper. So we just write here quantum chemistry. And now the definition via audio. Once again, quantum chemistry is molecular quantum mechanics and a branch of physical chemistry that studies the application of quantum mechanics to chemical systems. It uses the quantum properties of atoms. And so that was the audio definition, quantum chemistry. And we write here now the four quantum in quantum chemistry. Quantum numbers are what it is. 1, principal, 2, and this is not necessarily in order. Azimuthal, 3, magnetic, and 4, spin. Spin is usually denoted by S, and there's L, S, M, and P. Those are usually the letters used in the quantum mechanics and for quantum chemistry. So that's just a brief definition of quantum chemistry. If there's any addition, use the four letters here, L, S, spin, M for magnetic, and P for the principal. So the L must be for the azimuthal, M for magnetic, P for principal, S for spin. All right. So let us now go on to Maxwell equation. We'll return to some quantum mechanics, but it's going to be a little bit more complicated. So let's just draw a line here. Quantum chemistry. And so we move on to some introduction to electromagnetics here. And what we have is a Maxwell equation for electric field. And with this we have now the Faraday's law. Let's take note that B is the flux or the field by partial T. The Ampere's law let's take note that del is equal now to then we have a Gauss law and this is the differential form. This is for magnetic field. And this is the integral form. So this is the differential form. So the integral form is now for enclosed. Environment. So there we have our introduction, going back into solve these equations from way back there. Electromagnet is 232 and 332. City College Engineering syllabus there way back in the 1980s. But these law doesn't change really. Still the same. And let us now describe now the Hemholtz equation. And this was developed by Hemholtz. In 1870. And it's a linear partial differential equation of the form. It is a linear partial differential equation of the form whereby now is a Laplacian K is the eigenvalue and U the eigenfunction. Look at a brief look at the mathematical form of the Hemholtz equation, which is a linear partial differential equation of the form equals k squared u, where k is the eigenvalue, u is the eigenfunction, and del is the Laplacian. And this have application now in acoustic physics. One of the applications. This could see it have application in electromagnetics. Now the acoustic form takes the Hemholtz equation one over rho and like I said, I was going to continue here with something from the quantum chemistry here, and let's write it down. It's a determinant model called the Slater determinant. Quantum chemistry. And the Slater determinant this is chi, the Greek letter chi. Where chi is spin orbital. And is the product of a spatial function. molecular orbital. And the spin function alpha and beta. Alpha or beta. I think it's going to get a little bit complicated here with the quantum chemistry. So we take it from there. We have the Maxwell equation, the Faraday's law, Ampere's law, and the Gauss law in the differential, Gauss law, differential, and integral form. We have introduction to the Hemholtz equation and the Hemholtz equation for acoustics. And that was just the definition of quantum chemistry. So that will be that. Or quantum chemistry, quantum mechanics, and the interface of electromagnetics. We have quantum chemistry definition there, and we gave it in audio. We have Maxwell equation with Ampere's Gauss law and Faraday's law. Then we came on to introduction of Hemholtz equation and Hemholtz equation for acoustics. Then it came back down to quantum chemistry and the Slater determinant.